Welcome to another chemistry revision video. In this video we're going to be looking over the fifth and final topic in paper 1, energy change, so exo and endothermic reactions, and then if you're doing a triple science higher course we're going to go and look over chemical cells and fuel cells. Bit of a shorter topic, which is nice when compared with the previous four long and complex topics. So if you found this video and the previous four useful, please consider subscribing so that other people can find these resources more easily. Obviously it is only a few days before the actual exam, so now we're going to go and have a look at the advanced information. So for Combined Science Foundation, nothing here is going to be your major focus, but again nothing has been taken out, so there's a lot of higher stuff only in this video. So if you don't do that stuff, just do the stuff that's for everyone, including the required practical on how temperature changes, because that's going to be in your exam. Even if the actual theory isn't a major focus, you will get the required practical, so you do need to know about these reactions. So for Combined Science Higher, exo and endothermic reactions are going to be your major focus, and once again we see the required practical. That's going to be in everyone's exam. Chemical cells and fuel cells isn't actually in your course, so you don't need to worry about that. Triple Science Foundation, again, we see this exo and endothermic reactions as your major focus and the required practical, but chemical cells and fuel cells has been taken out completely of your exam, so you don't need to worry about that. And Triple Science Higher, or chemistry is a separate science, but I like to call it Triple Science Higher. Again, exo and endothermic reactions is your major focus, and the required practical is coming up in your exam as well. But chemical cells and fuel cells hasn't been taken out, so bits of it might come up, so make sure you go over that. So we're going to begin with 14 questions that everyone needs to know about energy changes, so if you want to pause the video and have a go at these. So the law of conservation of energy is very similar to the law of conservation of mass, really. The amount of energy you put into a chemical reaction, the amount of energy you get out. Energy is not created or destroyed. So it may seem like in some reactions, like when you're burning something, that lots of energy is being given out, but energy is not being created. The energy is being given out by the change taking place to form the reactants into the product. What is an exothermic reaction? Well, it's pretty much what I was just talking about. Exothermic is the one that releases energy and transfers it into the surrounding area, causing the temperature of the surrounding area to increase. So examples of exothermic reactions, well, combustion, like I was talking about, burning something that releases a lot of energy, that's very exothermic. You've got many oxidation reactions, so I think combustion really essentially is a form of oxidation reaction. So you just got to remember the vast majority of oxidation reactions, again we covered that in the last video, they're exothermic, along with neutralization reactions as well. So how do we use exothermic reactions in everyday life? Well, hand warmers, for example, you know, the ones where you open the packet and as air gets into it, that triggers an exothermic reaction that releases energy, and you can hold that kind of the reaction vessel in warms your hand. We also use it in self-heating cans. Now, I had not heard of self-heating cans before I even started putting this video together, but yeah, apparently they exist, so you can kind of open the can, I think, and what happens is an exothermic reaction starts, which heats the can, which is kind of useful if you're selling, like, I don't know, pre-made coffee, and you buy a coffee cup and you open the can and it starts heating itself up, and that's pretty cool, I thought. So endothermic reactions are pretty much the opposite. They take energy in from the surrounding area into the reaction, and that means that the surrounding area cools down because there's a temperature decrease because that energy is being taken in. Some examples of endothermic reactions, well, thermal decomposition. A complicated name, I know, but the name also kind of tells you what it is. Decomposition, but obviously breaking stuff down, and thermal heat. So thermal decomposition is when a compound is broken down by heat. Again, we discussed thermal decomposition briefly when we were going over salts and crystallization. Some salts thermally decompose. Another endothermic reaction, photosynthesis, which we look at in biology. And there's a third one on the specification, citric acid plus sodium hydrogen carbonate. You need to know that that reaction is an endothermic reaction. It has actually come up before, that reaction, oddly enough. Sodium hydrogen carbonate is also known as bicarbonate soda, so that cooking thing. You can react it with citric acid in an endothermic reaction. It forms carbonic acid. I don't think you just need to know that that is an endothermic reaction example. But obviously, if it asks you for an example, just go for photosynthesis. That's so much easier. So how we use endothermic reactions? Well, we can use them in like sports injury packs. You know, if at school you get injured, you go to the wherever you go and you get an ice pack. Or sports professionally, obviously you're not going to have a freezer close by where you can take out an ice pack. So sports injury packs, they make use of an endothermic reaction, and they kind of, when you start the reaction, it cools down really quickly and turns very cold, and you can kind of use it as an ice pack. That's kind of what they use in sport, especially when they don't have a freezer handy. Now we're going to get on to the required practical. This is coming up in everyone's exam. It's actually probably the simplest required practical in all of GCSE science, if I'm honest, because all we're doing is measuring the temperature change in a reaction. It's really, honestly, not that hard at all. So what we do is we put two. Well, obviously we're going to take one reactant. We're going to measure its temperature, preferably if we have both reactants at room temperature, 20 degrees C. That way we know it's going to be fair, and then we're going to add them together, stir them with a thermometer, and we're going to monitor the temperature change. We could like check it every 30 seconds or so, and then or just watch it and then write down when it gets to its peak, and then we can kind of see the energy change, because obviously when the reaction's finished, energy is going to be lost to the surroundings. And that's simply it. Obviously we need to talk about how we can minimize that energy loss, and also which variables you could be asked to measure. But this could come up, and they could use any reaction they put in the specification. They could use like all the reactions we talked about in the previous video, so metals plus acids, acids plus carbonates, neutralization reactions, metal displacement reactions. So check, if you see one of those come up, before you think, oh, it's going to be a chemical changes question, I need to talk about how the salt is formed. If it asks you for temperature change and energy change, then you've got to think more endothermic, exothermic, think more into this topic. But I'm going to go for question 10 before we go for question 9, because obviously we're not just going to measure temperature change for the fun of it. We're measuring temperature change. We need variables. Can you remember which variable we change? It's the independent variable. We need something to change, and therefore, obviously we're measuring the temperature, so that's the dependent variable. And so we could use mass, for example. We could add tiny bits of our reactants, see the temperature change, and then add a bit more, and then try different reactions and with different amounts, and see how that affects the temperature change. Or we could use different concentrations. So if we use dilute hydrochloric acid and dilute sodium hydroxide in a neutralization reaction, we could use then use maybe very concentrated hydrochloric acid. Obviously, may have to talk about safety issues around that. So wearing goggles, obviously, because you don't want the acid to get in your eyes, and then strong sodium hydroxide as well. That's going to be dangerous because strong alkali is just as dangerous. So yeah, concentration and mass you could be asked to as an independent variable. But essentially the method is the same, although in your method you have to talk about how you're going to minimize energy loss. So first of all, you might want to put both the reactants in a water bath, well obviously not in different beakers in a water bath, to make sure they're both at exactly 20 degrees C, to make it like fair. That could be a control variable, the starting temperature of your reactants, because obviously if you've been holding one of the beakers containing hydrochloric acid in your hand, then that hydrochloric acid is going to have warmed up, and there's not going to be a reliable, we don't say fair test anymore, we say reliable. So we want to make sure the starting temperature of the reactants is the same. We use a polystyrene cup because that's more insulative than a glass beaker. Obviously we look at this in physics. we'll put a lid on the top of the polystyrene beaker to keep as much heat in as possible, obviously with a hole in for the thermometer to go through. Then we could even go to the lengths of putting cotton wool or newspaper around your beaker. The more heat we can reduce, the more energy loss we can reduce, the more accurate our experiment is going to be, because we're going to see the true extent of the energy change without all the energy being lost. So to summarize, this method is very simple, just chucking it in a polystyrene beaker, making sure there's the same temperature beforehand in a water bath, obviously, putting a lid on, putting a thermometer through, and measuring the temperature change. So if it asks you to describe a method, you have to, it's very important, you really have to, for the higher marks, talk about how you're going to insulate and prevent energy loss, and it's probably going to come up as a separate question. So now we're going to move on to reaction profiles. I feel like question 14 is probably best relevant to answer first. Collision theory, it's more of a paper 2 topic, but I feel like it's very important here because we're talking about activation energy and there's a direct link between those two. So collision theory basically says that how chemicals react because when their particles collide with each other, and they have to have sufficient energy to react. So we really talk about that in paper 2, when we have our rate of reaction. It's all about how the particles collide, so how fast the particle is moving, and if they collide with enough energy. And that's what activation energy is. It's the minimum amount of energy that the particles must have to react together. So if you have two particles that collide, so let's take copper in cold water. If a copper collides with a water molecule, they probably aren't going to react. There's not enough activation energy in there because copper is too unreactive. But if we heat it up when the particles are moving faster and they collide with more energy, chances are you will actually get your metal plus water reaction there. Can you remember what that metal plus water produces? Maybe you need to go back and check the last video. So this is what we call a reaction profile. You may have to draw one of these for your exam. This is for an exothermic reaction, so I'll give it a label up there. On the y-axis we have the amount of energy, and the x-axis we have the time or the progress of the reaction. This really doesn't really matter, but what you can see here is this is how much energy the reactants we are putting in have. This is the energy that's stored within their bonds, and this little hump is the activation energy. You need to label this on. It's the amount of energy you need to put in to the exothermic reaction to give those particles enough energy to collide with each other successfully and react. And then the energy is released when we get past this point, and this is what we call the overall energy change between the energy of the reactants and the energy of the products. So in the case of exothermic reactions, it's energy released, and then this is the amount of energy that the products have. So as you can see, overall in an exothermic reaction, we can see that because the reactants have more energy stored inside their bonds than the products do, then we can see that energy is being released. And that is essentially how an exothermic reaction works. You need to remember how to draw and label these. You need to be able to label overall energy change and activation energy. And this one, probably energy on the y-axis. I don't know too much if the x-axis matters, because it's pretty obvious though, isn't it? I mean, you can't really forget it. So now here we can see an endothermic reaction. Obviously it's kind of different. We still have the energy on the y-axis, time on the x-axis, but obviously in an endothermic reaction the energy of the reactants is less than the energy of the products, and this means that we have an overall energy increase. So the overall energy change is the difference in energy between the reactants and the products, and in endothermic reactions we call it the energy absorbed, because the products have more energy in their bonds, so they're taking in energy from their surroundings. So energy is going in to break some bonds. Our activation energy here, the minimum amount of energy that the reactants need to kind of collide successfully, is more than the overall energy change in endothermic reactions. you need to remember that the activation energy for endothermic reactions is not just that little bit, because we're starting down here. They need this much energy. They need more energy than the total amount of energy stored in the products to start reacting. So if you're taking a foundation tier paper, that is everything you need to know from this topic. You're done, you can skip to the end. But for higher tier, we have some stuff on bond energies, which is kind of a slightly more in-depth look. I think it's a bit more exciting, makes a bit more sense, to be honest, on endo and exothermic reactions. So pause and have a go at these 6, although I have to say you can't do 4. You can't do these 3, so just wait until these come up and then pause and have a go. But have a go at these 3. So this is something you really need to remember. Energy is needed to break bonds, and energy is released when bonds are made. So this is quite a hard thing to get your head around, because I don't know, some logic might tell you that you need energy to put bonds together, but no. Think back to when we covered melting and boiling. As we increased the energy, that allowed the bonds between our particles to break and them to turn from a solid to a liquid to a gas. So it follows that the opposite happens when bonds are made. So when we form bonds, energy is released, and that makes bond breaking endothermic, because you're taking in energy to break those bonds apart, and that making bonds releases energy, because, like, imagine as you're cooling something down, it's forming more bonds. Then that releases energy, because those particles are no longer using that energy to move around as gases. They're kind of becoming more in fixed positions as liquids and solids. However, in chemical reactions, or in the majority of them, we have bonds both being made and broken, which means that the definition of endo and exothermic reactions is slightly more complicated. So in exothermic reactions, we have the energy released from bonds being made is greater than the energy being put in to break the bonds. And in endothermic reactions, obviously, more energy is needed to break the bonds than is needed to make them. So I like to imagine it as all of the bonds in all of the compounds, in all of the reactants, are being broken up down into their individual atoms, and then you put them all back together again into their new compounds. And obviously we go on to calculating the amount of energy in bonds. You get given the amount of energy in bonds, but you have to calculate it. So bond energy calculations. See if you can have a go at calculating the change in energy in the Forwards reaction of the Haber process. You've got the bond energies here. They'll always give you the bond energies in the exam, so you're going to have to calculate it. So first of all, we're going to write out the balanced symbol equation. But now here's the tricky bit. So you have to figure out which bonds are in the equation. So obviously this one we have bonds between nitrogens and hydrogens. Here we have bonds between 2 hydrogens. Here we have a bond between 2 nitrogens. It could be a single, double, or triple bond. So what we're going to have to do is we're going to have to go back to something we did in the second video, is to draw out the covalent bonding dot and cross diagrams for each, and then figure out which bonds we have, and then we can calculate it. So here we have the covalent bonding diagram for nitrogen. If you don't know how to do this, go back to the second video. But what we can see is we have 3 shared pairs of electrons, which means we're going to have a triple bond. And how many of those do we have? Well, we have 1 in our mole ratio. We have 1 to 3 to 2, so we have 1 of these. So what we will write is we will write that we have 1 of this, and how much energy does it have? 941. What do we measure the energy in? Interesting point. Kilojoules per mole. Here we have the covalent bonding for hydrogen. We have 3 of them. It's a single bond because there's 1 shared pair of electrons. So we're going to have 3 times the bond energy in kilojoules per mole, which is 436. So admittedly with hydrogen we could have just seen it was H2 and gone for taken 1 of these or 3 of these because we got 3 moles, but with compounds it's essential you draw them out Again, if you don't know how to do this, go back to the second video. We went through how to do dot and cross diagrams. So this is ammonia, and you can see we have 1, 2, 3 single bonds between nitrogen and hydrogen. So these are the bonds that we have in ammonia, and we have that is 391. So we have 3 times that, and we got 2 moles. So we actually are going to have 6 times that, which is 391. Can you remember what we measure them in? Kilojoules per mole. Very well done. Okay, so if you do the math, add these two together and do this one, we should get that we have 2,249 kilojoules per mole of bond energy on this side and 2,346 on this side. So now to see if it's exo or endothermic, what you need to do is you need to view all of the reactants energy, this energy on the left, as the energy needed to break the bonds. So that's your input energy, if you like. So you're inputting 2,249, and this is the energy that's being released when you're making the bonds. So 2,346. So if more energy is being released in making the bonds, then it's going to be exothermic, because exothermic is an energy release and therefore a temperature increase. So then to calculate the overall energy change, you kind of almost get rid of the this bit on the arrow, make it into a minus. You subtract the amount of energy needed to break the bonds from the energy formed to get your overall energy change. The answer to this is 97, or minus 97 I should say, because this value is the overall energy change. So if you imagine minus 97 on our reaction profile, it's going to be that drop, 97 less energy in kilojoules per mole, isn't it? So we're giving out 97 kilojoules per mole in energy. So I know that took a while and it looks complicated, but I hope you can kind of see that the method is really simple, like really, really simple. As long as you know how to do your dot and cross diagrams, it's quite fun actually. You find the bonds that you need, you multiply them together. So here we have 1, here we had 3, here we had 6, because it's just a lot of counting, and then you use your calculator to figure it out. And yeah, so it's not too hard. So here is the second example, the combustion of methane. Remember what we talked about, combustion is oxidation. You won't need to use all of the bond energies. They may well put some in to trick you. For example, they've put in the carbon-oxygen single, double and triple bonds, but I'll give you a clue, you only need one of them. So pause the video and have a go, see if you can do it. So here's the balanced symbol equation. And here are the covalent bonds. It's worth mentioning, obviously, they're all bonding to get a full outer electron shell of 8, apart from hydrogen, which wants a full outer electron shell of 2, because that's how big the lowest electron shell is. Go back to videos 1 and 2 if you're not sure about that. Now we can work out which bonds we need. So there's a single shared pair here, we've got double shared pair here, we've got double shared pairs here, and we've got single shared pairs here. And there we have our final answer, obviously remembering that this is the energy needed to be put in to break the bonds, and this is the energy released after making the bonds. So as this is greater, we have 808 kilojoules per mole of energy released, so the overall energy change is minus 808 kilojoules per mole, because if you imagine the reaction profile for an exothermic reaction, it goes down, doesn't it? So we have this overall energy change as being 808. So now we're going to move on to the final topic in chemistry paper 1. It's only going to appear in the Triple Science Higher exam. It's not in the Combined Science course, and it's been taken out of Triple Science Foundation. So we have chemical cells and fuel cells. Can be tricky to get your head around, but pause the video and have a go at these 16 questions, see how much you can remember. So this is an electrochemical cell. It might look a bit similar to electrolysis with our electrodes and our electrolyte. Can you remember what those two mean? Well, our electrode is a solid that conducts electricity, and an electrolyte is a liquid that conducts electricity. And what we have in our basic cell is we have each electrode is made out of a different type of metal, and our electrolyte contains ions that react with the metals at the electrodes, but they will react with the different metals differently. And because obviously we have ions in here and metals and the carrying of charge, this creates differences in charge at each electrode as the different metals react differently with the same ions, which creates a potential difference. A difference in charge between the electrodes, or a voltage. So we could put anything here. We could put a voltmeter to measure our potential difference, but this is just the wire where we can send off with our generated electricity, essentially. So there are many factors that can affect the voltage or the potential difference that's produced by the cell, but there's two main ones. First of all, the electrolyte used, so the ions in the electrolyte and how they react, depending on what ions they are, depends on the voltage. But the second one, probably the one you should probably remember, is the differences in reactivity of the electrodes, and this is where the reactivity series comes in again. If you have two electrodes with a large difference in reactivity, there's going to be a large potential difference in charge and therefore a large voltage created. So the bigger the difference in reactivity, the bigger the voltage made. So they could ask you to predict the voltage of the cell if they give you data of the voltage on other cells, but I really highly doubt that this is coming up, because this bit isn't a major focus, so you're only going to have like a small link question to both of these. Most likely you won't have a question dedicated to it, so a question like predicting the voltage of a cell won't come up, but I'll cover it just in case. Basically, what you can do is they might ask you what is the voltage created if the electrodes are magnesium and zinc, for example, and they might give you the voltage produced when both magnesium and zinc put with copper electrodes, and then give you the voltage produced. And basically, the difference in voltage produced gives you the voltage of the two new ones. Sorry, the two like magnesium and zinc. So you can think of it almost like a very simple simultaneous equation, if you like, but again, I highly doubt that's coming up, so I haven't really gone into it. I haven't given you an example because I simply don't think you'll need it. So a battery is simply two or more cells connected together in series. The reason batteries have greater voltages than cells is because we connect them in series. It means to find the total voltage of them, we can add up the individual voltages of the cells. So each cell kind of provides its own voltage towards the end voltage of the battery, because they're in series, not parallel. Again, rules of series and parallel circuits, which has actually been taken out of physics for us lucky triple science higher people. So as you know, with batteries, eventually what happens is they run out of energy. And why does this happen? Well, let's think. There's a reaction going on, isn't there, in the cell? The ions in the electrolyte are reacting with the metal electrode, aren't they? So eventually, one of the reactants is going to be used up completely, whether it's all the ions in the electrolyte are used up, or all the metal on the electrode is used up. But when that happens, obviously, if you lose one of the reactants, the chemical reaction can't happen, and therefore we can't generate potential difference, and we can't generate electricity. So that's why non-rechargeable cells stop producing electricity. Essentially, we have to chuck them away, get a new battery in, or get a new cell in. But we have been developing rechargeable cells and batteries recently. So what rechargeable cells and batteries use is they use reversible reactions, but not just any reversible reactions. They aren't reversible. They don't form a dynamic equilibrium and all that. What happens is they're only reversible when you put an external electric current into the cell, and that kind of stimulates the reaction to reverse. So all the products you've got sitting in your cell start reversing, turning back into the reactants, and so that when the battery is fully charged, we say basically the reactants, the ions and the metal, have both been their supplies have been topped up, which means that they can carry on going for longer. And that's what rechargeable cells and batteries are essentially, and that's why we kind of, I don't know, you plug your devices into charge, you're recharging the battery of them. And the specification does say you need to know that alkaline batteries are non-rechargeable, because of course their reactions are not reversible. So finally, fuel cells. Now these are tricky to get your head around, admittedly, but look, we've only got 5 questions on them, and then we get on to 3 nice, easy, factual disadvantage and advantage questions. So have a go at these. Fuel cells produce a potential difference, because what happens is into a fuel cell we put our fuel, and we also put oxygen. And what happens to the fuel, let's say hydrogen, because we're looking at our example of a hydrogen fuel cell. Our hydrogen gets oxidized by the oxygen electrochemically within that cell, and this produces a potential difference in the cell. So here's our hydrogen fuel cell. Okay, I know it may look complicated, but we're going to talk through it step by step. So we first of all, which should probably be noted, we have our electrolyte here. It's usually an acid because it supplies H+ ions, and hydrogen and oxygen are our inputs, water is our output, and we have our anode and cathode. Be careful though, unlike electrolysis, they aren't clear-cut positive and negative. So what we do is we put hydrogen into the anode compartment, and the anode compartment is initially negative, so it attracts the hydrogen atoms, which are essentially just protons, and the hydrogen is oxidized, so it loses its electron, and it forms a H+ ion, so it's attracted, the positive H+ ion is attracted to the negative anode. Meanwhile, the cathode is positive, so what we get is we get these the electrons that have been lost from the oxidation of hydrogen. They flow through the wire, and this is where we can kind of get the potential difference from. By the way, the electrons flow through the wire to the positive cathode, and as the electrons kind of flow through it, it kind of turns it negative, so that the H+ ions in the acid electrolyte are then attracted to the cathode, and they travel through this membrane here to go into the cathode compartment. And we also have our oxygen being inputted into the cathode compartment. So what we have is we have a mix of H+ ions, oxygen, and electrons in the cathode. And because oxygen is a non-metal, it has 2 gaps to fill on its outer shell. It gladly takes the electrons given to it, and it becomes reduced. So obviously it gains electrons to fill its outer shell. It also reacts with the H+ ions, and this combination of 3 ends up forming water, which is why we get water out. But you need to know that essentially a potential difference is created. So let's run through it again quickly just to be sure. So we get our hydrogen in to the negative anode, and what happens there is our hydrogen is oxidized, it loses electrons, and the positive hydrogen atom, because it's just simply a proton, binds to the anode, and the electrons go off here because they want to go to the positive cathode, and it's this difference in charge that creates our potential difference. But then we have to add our oxygen in here to prevent the cathode from becoming negative due to all the added electrons, because then charge wouldn't flow because both sides would be negative. So we add oxygen in, and this takes up the electrons and is reduced. And because we have our electrons in here, the H+ ions are also attracted to the electrons, so they come through this membrane. The H+ ions are from the acid electrolyte, remember, not from the anode. So these H+ ions come from the acid electrolyte. They go in, react with the oxygen and electrons to produce water. So essentially our inputs are hydrogen and oxygen, and our outputs is water. So we could write a chemical equation for this. So this is essentially what's happening inside here. I should put disclaimer, I'm not an expert in these. Something that I've said in the past 5 minutes is probably scientifically incorrect, but at the same time, it's you don't need to know every scientific ins and outs of this for GCSE level. What you really need to know is that the hydrogen goes in, becomes oxidized. This flow of electrons from the negative anode to the positive cathode creates this charge because we have a potential difference. The oxygen comes in and reacts with the electrons and the H plus ions from the acid to create water. That is kind of all you need to know. Like, this is a complex bit of chemistry, you know. This is hard to get your head around. This like kind of top scientists engineering kind of stuff. But going back down to GCSE level, what do we have happening in here? Well, here we have oxidation and here we have reduction. So we can write half equations. That's a GCSE thing. So have a go at writing half equations. You should be able to do one for the anode, but the cathode one might be a bit hard because you have all these free coming in to react and produce water. So here's our equation for the oxidation of hydrogen at the anode. We have H2 coming in, so we have to balance it because hydrogen is diatomic. So we get H plus ions and obviously the electrons that go off up and form our flow of electrons. So this one, the cathode, it's kind of difficult, you just have to learn it. But it's, to be honest, at the same time, you can kind of remember we've got three reactants, if you will, coming in: oxygen, O2 diatomic, H plus ions and electrons, and we're getting water out, so then we just need to kind of balance it, and this is how we balance it. Sorry, I'm missing a 2 here, and I think that's, yeah, yes, that's it balanced. It's not too dissimilar for the reduction of OH minus ions back in electrolysis, but at the same time, don't get confused between those two half equations because they are different. So make sure you learn them both separately. And finally, you need to know that because we've got oxidation and reduction going on, hydrogen fuel cells therefore make use of a kind of redox reaction. Oh, well done for making it through all of the challenging fuel cell stuff. Now we just have to evaluate the advantages and disadvantages of hydrogen fuel cells. So first of all, two disadvantages of using petrol. This should be pretty obvious. Well, the first one, of course, it emits greenhouse gases like carbon dioxide, which go into the atmosphere and cause climate change, global warming. But also, petrol and fossil fuels are non-renewable, which means that sooner or later we're going to run out of them, and then we're going to have to rely on either electric battery-powered cars or hydrogen-powered cars. So an advantage of using hydrogen-powered fuel cells would probably be that they store more energy than electric battery cars, so you would have to take your battery-powered cars to be recharged more often. I know we're like developing batteries that can store more energy, but that's kind of a project for the future at the moment. Our hydrogen fuel cells can store more. The batteries, they're very polluting and bad for the environment when we dispose of them because they're made of lots of toxic metals, and unless they're properly disposed of, they can be very polluting, and often they're not properly disposed of. And also, unlike hydrogen fuel cells, batteries in electric vehicles, there's a limit to how many times they can be recharged, and then they'll need replacing, and that can become very expensive, whereas hydrogen fuel cells are less so. However, there are some problems with using hydrogen fuel cells. It's not the miracle solution. We do have a few major problems. First one, hydrogen and air react. Hydrogen's explosive when it reacts with air, so we have to like compress it to store it safely, and that can get a bit complicated, especially with the risk of car crashes and, you know, massive car explosions if you've got loads of hydrogen compressed in the back of your car. There's also the factor that hydrogen takes up so much more space than batteries because you have to store it as a gas, and gas, obviously, that takes up a lot of space. So that could even cancel out the fact that batteries store less energy, because while we can store more energy using hydrogen fuel cells, storing the actual hydrogen, we can't actually store that much of it in the car. And probably the biggest problem, there's two main ways we get hydrogen, and both of them need energy. And we've got to get that energy from somewhere, and often it comes from fossil fuels, which just kind of takes the whole problem of petrol and diesel cars and puts them elsewhere, hides them under the sustainable title of hydrogen fuel cells. Basically, we can get hydrogen from electrolysis of water, like we discussed in the last video, but that needs energy. That energy may well come from fossil fuels. If it comes from renewables, then fine, sure, that's good, but often it will come from fossil fuels. And the other way to get hydrogen from fossil fuels is by breaking down the fossil fuels themselves, because they're hydrocarbons. They contain a lot of hydrogen, so we can break them down into and take the hydrogen from them. So they're definitely not perfect and a work in progress, but maybe in the future we'll see more hydrogen fuel cells as these disadvantages get ironed out. So there we have it. It was a pleasure to record a video less than an hour long. I know that chemistry, there's so much stuff in it, so much stuff to understand, but hopefully, especially if you're not triple science higher, there wasn't much stuff to learn in this topic at all. Again, revision. The chemistry exam is fast approaching, only a few days away now, so do these questions maybe just now. Maybe if you've just done them, then note down all the ones you got wrong. Anything you didn't understand, you want to come back to tomorrow, or if you want to kind of do them the night before, maybe if you do go through them and then look up some exam questions to do as well to kind of test your understanding. And obviously just remember to go back through the ones you got wrong, because that's how you're going to learn. And then here are the questions on chemical cells and fuel cells if you're doing triple science higher. So I hope the reams of chemistry revision that I've just churned out has been helpful, both in this video and the previous four. Yes, there's a lot to understand in chemistry, but once you kind of understand that, it all kind of clicks. And it's actually kind of quite fun to go through the exam questions and go, yes, I understand that, I know why, and I know how. And you can really get a full understanding of the paper and go for a grade 9, hopefully, or definitely an amazing mark. So yeah, I hope this has helped you towards that goal. Please subscribe if you did find it helpful, and I wish you all the best of luck with your chemistry exams.